So section 2.5 is about limits at infinity. So this is what the graph looks like, the y values, as x goes to plus or minus infinity. That's what the limits at infinity are. They describe y values as x approaches plus or minus infinity. And that's known as the end behavior of the graph, because it's what happens at the left and right ends. Sometimes these are horizontal lines, and they call them vertical asymptotes a lot of times when they're horizontal lines. But this just lets you know what the graph looks like when you go far out to the left and the right. And there are some properties that we know. The first one here, these are from the book here. The first one says that as x goes to plus or minus infinity, if I raise x to a power, that's like putting infinity into some power. I want to get infinity out when I do that. And if n is even, that means I'm raising it to an even power. So whether I stick plus infinity or minus infinity in here for x, the negative will be taken care of if n is an even power. So an example of number one might be the limit as x goes to infinity of x to the fourth. If it's an even power, it doesn't matter whether it's a plus or a minus infinity. The fourth power will make the negative go away. But that's not true if n is an odd power, and that's what the second case says. If n is an odd power, then when I go to positive infinity, I'll get infinity out. Infinity to the third is infinity. But if I go to negative infinity, the odd power there will let the negative stick around. So as x goes to negative infinity, the y value goes to negative infinity. That's the idea when n is odd. Here's an example with an odd value for n. The third property here says that if x goes to plus or minus infinity, 1 over x to any power goes to 0. And that makes sense because if you think about an example, the limit as x goes to infinity of 1 over x, that's n equals 1 because it's the first power. Think about what happens when I plug in numbers for x. Remember, x is getting bigger because it's going to infinity. So I'd have 1 over 10, 1 over 100, 1 over 1,000, 1 over 1,000,000, 1 over 1,000,000,000. Those numbers are getting smaller and smaller and approaching 0. And it doesn't matter what power this thing has in the denominator. That same property occurs. The fourth property here says that if you have a polynomial, like negative 4x squared plus 5x plus 1, then if you want to determine the end behavior at plus or minus infinity, all that you have to look at is the highest power term. Because when you're plugging in huge numbers for x, the highest power term grows the fastest. So it ultimately determines the end behavior of the graph. And here are transcendental functions. These limits we know just because we know what the graph looks like. The first one is talking about e to the x. And the graph of e to the x goes to 0 when x goes to negative infinity. That's what the second one says. And the y value goes to infinity as x goes to positive infinity. That's what this first one says. The graph of e to the negative x is very similar, except it's flipped across the y-axis. So you'll notice as x goes to infinity, the y value goes to 0. That's what the first one says. As x goes to negative infinity, the y value goes to infinity. The natural log graph has a vertical asymptote at x equals 0. And so you'll notice that from the graph, as x goes to 0 from the right, the y value goes to negative infinity. As x goes out to the right to infinity, the y value slowly grows to infinity. So those are just properties that we have to remember about the end behavior. Those 6 there are really 3 graphs that they're getting them from, and they're transcendental functions. So at the moment, we really can tell this mainly from their graph. But let's practice analyzing some limits at infinity. So the first one is the limit as x goes to infinity of 3 plus 10 over x squared. Well, I can break that limit up across sums. So that's the same thing as the limit as x goes to infinity of 3 plus the limit as x goes to infinity of 10 over x squared. Now this first one has no x's to plug in. So no matter what x goes to, all you get out is the number 3. Because I can't plug infinity in anywhere. It's just the number 3. So as x goes to infinity, the number 3 stays the number 3. Now this second limit has a 10. We know that 1 over x squared would go to 0 from the properties above. This is 10 over x squared. That should go to 0 too. you don't necessarily have to write this next step like I'm going to, but I can take that constant and factor it outside the limit. And the reason I'm doing this step is so it's easier for you to see exactly where I'm getting this next limit from. Notice this limit here, from above, if you look at the properties, the limit of 1 over x squared as x goes to infinity, that limit is 0. And we know that from the property above, property 3, the limit of 1 over x to a power equals 0 as x goes to infinity, plus or minus. So here this thing is going to end up being 0. And we get that this limit is 3 plus 10 times 0, which is just 3. I would have been okay if right here you realize that limit goes to 0. This step here you didn't necessarily have to write. You could have gone from here to there and solved the problem. Well, let's try it again. Here's another limit as x is approaching infinity. 3 plus 2 over x plus 4 over x squared over x squared. In a perfect world, we could plug infinity in, but the problem is I would get infinity on the top and infinity on the bottom. And I don't know what infinity over infinity is. Is it 1? Is it infinity? It's an indeterminate form. So to do this limit first, I'm going to break it up. This is actually 3 fractions, and you can write this as 3 separate fractions that all have a common denominator. 3 over x squared plus 2x over x squared plus 4x squared over x squared. Notice if I add them all together, the common denominator is x squared, and I would add the numbers on top. And I can simplify this if I want. This is the same thing as the limit as x goes to infinity of 3 over x squared plus, I can break the limit up by the plus and minus signs. I can cancel an x here. 2x over x squared is the same thing as 2 over x. And that last one, when I cancel the x squareds, I just get a 4. Well, we know that if there's x's left on the bottom, that limit goes to 0 as x goes to a plus or minus infinity. Since x is going to plus or minus infinity, this limit will be 0 because you have powers of x left on the bottom. And this last one, there is no x's to plug in. So the limit as x goes to infinity of 4 is just 4. Now problem 3 is an example of a squeeze theorem problem. We know that the cosine of x is bounded between -1 and 1. If you go back and look at your trig, or at least look at the unit circle, you can see that the cosine values from the unit circle are numbers in between plus and minus 1. So I can use the squeeze theorem here. And a lot of times they do the squeeze theorem with sines and cosines because it's easy to bound it. Sine is also bounded between plus and minus 1. So I know that -1 over x squared is less than or equal to the cosine of x over x squared. And that's because -1 is less than or equal to cosine. And this is less than or equal to 1 over x squared. That's because cosine is less than or equal to 1. And I can take the limit of all 3 sides of the squeeze theorem I've set up. And I get the limit as x goes to infinity of -1 over x squared, less than or equal to the limit as x goes to infinity of cosine x over x squared. This is what we're trying to find. We don't know any special things about these trig these trig limits yet. So I use the squeeze theorem, and I take the limit of all 3 sides of that. And even though I can't take the limit of what's in the middle, I can take a limit of what's on the left-hand side and what's on the right-hand side. Notice that that limit, the limit as x goes to infinity of -1 over x squared, that goes to 0 because you got 1 over huge numbers on the bottom. And this limit over here, the limit as x goes to infinity of 1 over x squared, that goes to 0 as well. That's property 3 from the list above. And so I have 0 as less than or equal to the limit as x goes to infinity of the cosine of x over x squared, which is less than or equal to 0. And the only number in the whole world that could make that work is the number 0. So we've proven from the squeeze theorem that this limit is 0. We've squeezed it between two functions we know. So a squeeze theorem example, and this is a squeeze theorem that you should pay attention to because it shows up a lot. If ever you have a sine or a cosine on top, remember sine and cosine, those are the only two, are bounded between plus or minus 1, and so it's really easy to use the squeeze theorem when sines and cosines appear like that. It's a trick they like to play. And the last two are polynomials. Here I have the limit as x goes to infinity of 3x squared minus 9x to the 7th. Well, since it's a polynomial, as x goes to infinity, the only thing I have to worry about is the highest power term, which in this case is 3x to the 12th. Well, when I plug positive infinity into x to 12th, I'll get other positive, really big numbers. And when I multiply them by 3, they're just bigger. They stay positive, though. So this limit here works out to infinity because the limit of the leading coefficient, the highest power term, gives me infinity. This one here is a little bit tricky. Let me rewrite it. I'm going to factor the negative 12 out. And a lot of times it's safer to rewrite it so negative exponents are gone. I can rewrite x to the negative 5th as 1 over x to the 5th. That's what x to the negative 5th means. And when I do that, I notice, or at least it's easier to notice, that that limit is 0 by that property 3 above. And so this limit is negative 12 times 0, which is 0. So it is usually easier if you can take negative powers and rewrite them as fractions, because it's easier to recognize where those zeros are in the limits. So I should circle my infinity. Now there are a couple cases that happen that aren't solved that way, rational functions. These are fractions. That's what rational functions are. And if you have rational functions, the trick to do those, there's other tricks we'll learn later, but the trick to do those now is to divide every term in the top and the bottom by the highest power in the bottom. Because the idea is to get all the x's on top and see what happens. That's why we want to kind of just divide them all out of the bottom. It's easier to judge what that limit will be. So here I have the same function. X is just going to positive infinity in A and negative infinity in B. So let's just really look at what happens when I divide the highest power term, or when I divide the top and the bottom by the highest power in the bottom. This function, the highest power in the bottom, is x squared. So what I'm doing is I'm multiplying the top and the bottom by 1 over x squared. In effect, that's what I'm doing. 1 over x squared divided by 1 over x squared is just the number 1. So I didn't change anything by doing that. But when I distribute this in, what it does, in effect, is divides every term by x squared. I have 6x squared over x squared minus 9x over x squared plus 8 over x squared. I have to redo that one. That's what I did on top. 1 over x squared means multiply the numerator by 1 and divide by x squared. On the bottom, I have 3x squared over x squared plus 2 over x squared. And this is a legal move because what I really did was multiply by the number 1, even though I wrote the number 1 in a really, really, really strange way so that I could simplify stuff. But after I've done that, now I'm just going to simplify this fraction. This is the limit as x goes to infinity of 6 minus 9 over x plus 8 over x squared. And on the bottom, we have 3 plus 2 over x squared. Now when I work this limit, anything that has x squareds on the bottom goes to 0. It doesn't even matter if the x goes to plus or to minus infinity. So it doesn't matter if I put a plus or minus here. These terms that have x's in the bottom are all going to go to 0 from that property 3. So in this example here, I get the limit as x goes to infinity of 6 over 3, which is the number 2. That's for part A. The limit as x goes to infinity is 2 in part A. Now if I do part B, everything is going to be exactly the same, except this very last part here. You can imagine the exact same stuff with a negative infinity in here. 6 minus 9 over x plus 8 over x squared. I would still have to divide everything by the highest power in the denominator. So this step would have happened right here in part B. And from this step, I would have gotten to here. It's the same thing we did when we right here. It's the same simplification. But it doesn't matter whether x goes to plus or minus infinity. These terms with x's on the bottom would still go to 0. And I would still be left with the limit as x approaches negative infinity of 6 over 3, which would also be the number 2. So here, parts A and B would have the exact same answer, and I would have done the exact same thing to solve them. So in this case, it didn't matter whether it was a plus or a minus infinity. The limit in both cases was a 2. And since this would be a constant y value, this would be called a horizontal asymptote. They call them horizontal asymptotes of rational functions. Well, let's try some more. Here's another. The limit as x goes to infinity of 40x to the 5th plus x squared over 16x to the 4th minus 2x. I'm going to divide everything I see by the highest power in the bottom. In this case, it's x to the 4th. And so by doing that, I really just end up dividing everything by x to the 4th. So you can go straight to the second step if you want to. And I'm just going to divide every term on the top and the bottom by the highest power in the bottom, which is x to the 4th. And I simplify. I cancel x's. And what I end up with is 40x plus 1 over x squared over 16 minus 2 over x cubed. And since x is going to plus or minus infinity, 1 over x squared goes to 0, and 2 over x cubed goes to 0, because x is going to infinity. And that's that property 3 again. So this is the same thing as the limit as x goes to infinity of 40 over 16x. That x is on top. So as x approaches infinity, I plug in infinity for x, and I get 40 over 16 times infinity. Anything times infinity stays huge. Infinity is increasing without bound. So this limit works out to be infinity because I have x to the first power here. That's the first property of those limits above. So here's a function that has a infinite end behavior, positive infinity as x goes to infinity. And here's some just other versions of this, or their grosser versions. This is the same function. I'm going from plus infinity first and minus infinity second. And here it's hard to find the highest power in the denominator is all. But if I look at the bottom, I notice that 2x cubed is here. And they say, well, what's the highest power here? Well, this is x to the 6th, and it's the square root. Well, what would the square root of x to the 6th be? The square root of x to the 6th would be x to the 6th to the 1/2 power. That's what the square root is, the 1/2 power. And you multiply when you take the power of a power, you get x to the 3rd. So the square root of x to the 6th, which is the highest power in here, becomes x to the 6th to the 1/2, which is x to the 3rd, which is also the highest power. So in here, the highest power is x to the 3rd. So I'm going to divide everything by x to the 3rd. Now there's a little bit of an issue that arises when I do this. On the top I have 4x cubed plus 1, and I'm going to divide it by x to the 3rd. That's the highest power in the bottom. And on the bottom I have 2x cubed plus the square root of 16x to the 6th plus 1. And I'm going to divide those by x cubed as well. And I can simplify most of this. That's just a 4. That's 1 over x cubed. That's just a 2. But wait, what's that? I can't stick them together to simplify them. So instead of writing it as x to the third, I'm going to write it as the square root of x to the sixth. If I write it that way here, I'll be able to combine these radicals and simplify. So this thing works out to be the limit as x goes to infinity of 4 plus 1 over x cubed. On the bottom I have 2 plus, I can put both of those square roots together over a single quotient, 16x to the 6th over x to the 6th plus 1 over x to the 6th. And I can simplify that further. The limit as x goes to infinity of 4 plus 1 over x cubed over 2 plus the square root of 16 plus 1 over x to the 6th. Now, since x is approaching infinity, the 1 over x to the third will go to 0, and 1 over x to the 6th will go to 0. But that's why we rewrote x to the third as the square root of x to the 6th. So we could stick it together under one square root and just divide each term. And so this limit becomes the limit as x goes to infinity of 4 over 2 plus the square root of 16, which is 4 over 2 plus 4, which is 4/6, or 2/3. So that's a tricky one because the highest power in the denominator had a square root of x to the 6th in there, and you had to reconcile the fact that that was the same as x cubed. Now the second part of this problem, part B, is the same thing except I want x to go to negative infinity. Notice, if I go back here and just change all my infinities to negative infinities, this will make it problem B all of a sudden. It's magic. That's why whiteboards are so nice. You can just erase it. So I'm going to change all my infinities to negative infinities and see if anything would be different if I did that. Nothing would be different here because I didn't even really find the limit. And here I didn't find the limit either. This third step I actually found the limit. I said the limit of 1 over x cubed goes to 0, but that's true whether x is plus or minus infinity. The limit of 1 over x to the 6th goes to 0, but that's true whether x is plus or minus infinity. So that's still a true statement as it sits. And that means I can still get 4 over 2 plus the square root of 16. So I get the same limit for both of these. Because everything would be done exactly the same, and these limits here would still go to 0, because that happens regardless of whether x is positive or negative infinity. So they have a couple scary ones like that in the book, and you just have to be careful with finding the highest power. The last one has to do with one of the transcendental functions we talked about before. This is a limit you just have to remember from the graph. And to help you visualize what's happening, here's a picture of e to the negative x. Well, if I took all the y values and multiplied them by -3, it would flip this thing across the x-axis and scale it. So you can kind of see as x goes to infinity, this thing is going to go to 0. This is kind of what the graph is going to look like if you could draw a picture of it. But let's actually use the limit laws that we learned above. I can factor the -3 outside of the limit. And if you look above on the transcendental functions, as x goes to infinity, the limit of e to the negative x goes to 0. You can memorize that. But you can memorize one thing instead of two. I can write e to the negative x as 1 over e to the x. And a lot of times this is how people will remember it. E to the x goes to infinity. So e to the negative x goes to 0. So this limit right here is going to be 0 by the properties above, although some people rewrite it like this to recognize it'll be 0. But in either case, I get -3 times 0, which is 0. And if you look at the graph, you'll notice that. As x goes really far to the right, the y value looks like it's approaching 0. So that's the idea of evaluating limits at infinity. Limits at infinity are horizontal asymptotes, but they describe the end behavior of the graph.